Okay, so let's get started. This is our last proper lecture. It has been a long way, and we're going to talk about generative adversarial networks. The next two lectures we have remaining are going to be just project presentations. So it's going to be your turn to take the stage and do and present your work for us. Okay. This is not updated. My bad. So last time we were talking about variation autoencoders, but then we started with autoencoders, right? And then as we talked about two types of autoencoders: denoising autoencoders, and masked autoencoders. And then we saw variational autoencoders. And all of this was part of our discussion of generative modeling. And we're going to keep this discussion. But here we also saw KL divergence as a regularization term that we add to the mean square error to force our distribution to have 0 mean and 1 variance. And today we're going to talk about I really forgot to update this. Generative adversarial networks. And this will include problems with VAEs. Then we're going to talk about generator itself as a CNN, then the discriminator also as a CNN, and then we're going to talk about adversarial training and some improvements of GANs over the years and some results. All right. So in this image, I'm showing a result from a variation autoencoder. As hopefully you can see, this is a 1, so we can tell it's a 1, but it's a blurry image. I think on the slide here, it doesn't look very much like a blurry image, but if you look at the PDF later, you'll see that. And this is a characteristic that normally happens with VAEs. They tend to give us blurry images, and that's because of the loss we use. Mainly because the MSC loss here that we use with the KL divergence, plus this idea of learning an explicit distribution, it generates this behavior. I think intuitively what you can imagine is that one of the best ways to minimize mean square error is to actually take the average of the images that represent ones, for example. And if you average multiple images, in practice, you're going to get blurry images. Okay, and this is it's a known problem. And there's in fact even kind of improvements of VAEs that try to help this solve this problem. We didn't talk about this, but there is, for those of you who are interested, there is the VQ VAE, okay, which stands for vector quantized VAE. We actually talked about vector quantization in a couple of lectures ago, which is this idea of having a vector in a continuous space and then map it to discrete space. We saw that we can make a kind of a one-hot encoding and have a code book that we use to get the discrete versions of any given continuous vector. So VQ-VAE actually uses this idea of a code book and together with VAEs to try to improve image quality. So there is actual improvements over that. Here, if you look at the paper, it's pretty much that idea of they add in between the encoder and the decoder, they have a code book that is learned throughout the process. And they will show as a result that they get better images out of this. And this is a work from 2017. And if I'm not wrong, the DALL-E 2 model from OpenAI was based on some sort of VQVAE back in the day. But the point that I want to make here is that if you remember the loss function of VAEs, which is just a mean squared error plus a KL divergency, we are not explicitly encoding like image quality here, right? Ideally, we should have some sort of mathematical formula that represents how good an image is, and we want to put that in the loss function, right? Because then we would optimize for that loss function. Let's say, oh, this is a good image of a cat. If I knew how to do that, I would put that in my loss function and make my generator somehow or minimize or maximize the metric. So then I would actually produce high quality images. But the point is, how do you actually formulate that, right? There is no, we don't know how to do that, like how to evaluate images with a metric. And so, but there is a solution to that, and that's the intuition behind GANs. They're going to try to explicitly evaluate the quality of the produced output. And how do they do that? So here's like a diagram of a GAN. And a GAN has two parts, similarly to VAEs. In VAEs, we had an encoder and a decoder. Here, they're not called that, but there is some similarities. So a GAN has two parts, and they are two separated networks, a generator and a discriminator. And for now, don't worry about how we actually implement them. They're just two separated networks. And the point that I was trying to make is that now what the discriminator is going to do is it's going to classify images in a binary way. So basically, you try to separate real images from fake images. So now I have a classification problem where imagine I have a set of real images that I collected, maybe taking pictures out there of cats, let's say. And I use a generator to produce the same amount of pictures. But now they are all fake. I know they are fake because I produced them through the generator. So they are synthetic or fake, right? If I feed them to the discriminator, I want the discriminator to separate them apart and say like, oh, this is a fake image and this is a real image. Okay? And the trick here is that if you train these two networks together, what I want to do is to make my generator better at the same time that I make my discriminator better. And if I keep doing that in a loop, so I'm going to make kind of a game where I first make my generator better, and then it makes it hard for the discriminator to separate the images. But then if I train my discriminator, it gets a little bit better at separating the images. So now I restart the procedure, and now I try to generate images again. But because my generator has gotten a little bit better, it's a little bit harder for the discriminator. So if I keep doing that, so this is going to converge towards a discriminator that cannot separate the images anymore. And the generator is going to actually generate fake images that look like realistic images. Okay? So it's a completely different procedure. So initially, the generator just generates random noise. But then over time, this noise starts to look like real cats, for example. And this is really clever. And this has been a seminal paper from Ian Goodfellow and others, published in 2014. And the title is just Generative Adversarial Networks. By the way, this paper has been awarded this year because it has been now 10 years from this paper. And NeurIPS, which is one of the most important deep learning conferences. I think it's Test of Time Award or something. They announced last week 2 papers that won this award that these papers have survived the test of time because they have been useful up to this day. And this paper is here. generative adversarial nets. Only 2 papers got this award this year. This one is, we talked about this. This is like sec-to-sec models for machine translation. And this one is just for image generation of GANs. And there is one part here I didn't talk about, which is as similar, this is similar to VAE. So we have to give an input to the generator, right? We cannot produce anything, right? There's no way to start a network from no input, right? So the way we start the generator is normally with a Gaussian noise or any type of noise, okay? That is, and then from this noise we're going to produce images, and then we're going to train these 2 networks, and these images are going to go through the discriminator together with the real images, and then we're going to do this kind of game type of training to, over time, get the generator to produce realistic images. Okay, but let's get to the details, right? So in practice nowadays, especially after 2015, 1 year later, the release of the initial GAN, Radford, we have seen this name actually if you have paid attention to the references, this name has been also like very popular in my slides. Radford, Alec Radford is from OpenAI, and he's behind like these works on GAN, is also behind the GPT model and others. So he has been very influential. I think he's also a cool person because he doesn't have a PhD. He's just like a software engineer, but he has contributed to science a lot. Anyways, so since 2015, we typically implement the generator as a convolutional neural network. So we start with a Gaussian noise, which is a vector. You can think of this as like having 4 dimensions or 100 dimensions, but it is a vector. And what we do is we're going to use those transpose convolutions that we saw last lecture to upscale this vector to an image. But before we start this transpose convolution, by the way, this fractionally strided convolution is another name for transposed convolutions. Okay, so when you see this fractionally strided convolution, that's how they call it in the paper, but it's exactly the same thing. And also, people also call these operations deconvolutions. So if you see these 3 things are the same. But first thing you have to do is this initial step here, that you have to somehow transform a 1-dimensional vector into a volume. And the way we do that is we first pass this through a linear layer just to have more features. Okay, so imagine we start with a z vector with 4 dimensions, and I project it to a 16 dimension with a W matrix. Okay. Now I simply reshape this 16 by 1 vector into a volume. So if you look here, there's 16 dimensions. The first 4 here are part of the first filter. The second 4 become the second filter. The third 4 become the third filter, and the last 4 become the fourth filter. So that's how I start my first volume. Okay, I just reshape this big vector to get the shape I need. And then I keep applying transposed convolutions until I get to a volume that is W by H by 3, assuming that I want a certain width of image, a certain height, which is H, and 3 channels because RGB. Okay. So if you look here at the last layer of the generator, here it's a 64 image by 6, so it's a 64 by 64 image by 3. So it's a 64 by 64 colored image. Okay. So just have to make sure the last layer here has 3 channels, because I need to map this to an actual image. So if you look at any of these upscaling architectures or networks that and this would be the same for VAEs, for the decoder. The VAE decoder could be implemented like this. Okay, there we don't have a We have a sampled z, it's the same problem. But this sampled z comes from the distributions, right? So it's exactly the same idea. The generator here could look like a decoder of a VAE. And the pattern is you have smaller, in the early layers, you have smaller width and height and larger depth. And in later layers, you have a bigger width and height and smaller depth. So it grows in size and decreases in depth. That's the, as we normally would see. So this is the opposite of what we normally see with a convolution, where we start with less depth, more size, and then we have less size and more depth in a regular convolution. Okay, is it clear how we actually produce this this image? Okay, so now we can make an image out of a z vector. So, all right, that's all from the generator. And the discriminator is a symmetric architecture. So now we have to take an image as input. It could be either a fake or a real image, but it takes an image as input, or a batch of images, right? But then, so it's a 64 by 64 by 3 because of RGB. And then we use a regular, this is a regular convolution neural network to extract a feature vector at the end. And then this is a binary problem. So at the very end here of the CNN, we're going to have a sigmoid activation function because I have two labels only. And I'm going to give the probability of being real, let's say. So that's it. Now you have the generator and discriminator, and the trick or the most interesting things here are like how you actually train this network. Let's see. Okay, yeah, just a couple. So just some details. In practice, you're gonna feed. I'm showing here 3 real images and 3 fake images, because normally when you're training the discriminator, you're gonna make a mini batch that has k real images and k fake images. So you have a balanced mini batch, and then you update the weights based on this balanced mini batch. And these real images come from the data set. Okay, so we assume you have a data set of images that you know are real because you took them or something, or you took from the internet, right? So they are real images. And here you just take images from the generator that initially are just random. Okay, so let me give you a geometric intuition of what's going on so far. So the generator, or mathematically, is implicitly modeling a conditional distribution P of x given z. Z is our random noise. X is the distribution of the, X is the images themselves. So here the trick is that we are assuming that there exists some features z that are latent that represent the real data. So this is actually how most of these models work. They assume that there is some latent representation that somehow magically represent the images. So there are features that I don't know. So I'm going to assume that there is a feature vector that represents the image, and I'm going to try to decode or generate from this latent vector. And then I let the model learn these latent representations, okay? So most of these generative models somehow, they do something like this. And there is a whole theory behind like generative modeling that is way more mathematical that I think we should get into here. And there is theoretical foundations, that's the point I'm saying, for modeling this way, okay? And there is, one of the most harder things here is actually to, when you try to approximate distributions, numerically you get into a lot of trouble. Because this very, very quickly gets intractable, because when you're talking about probability dense functions, or density function, sorry, you have to compute integrals most of the time. And then it becomes intractable to train these models. So we have to always approximate things when you're doing generative modeling with neural networks, because we need to train them with gradient descent. So there is a lot of like problems that get into like this idea of modeling a probability distribution directly. Anyways, that's enough. If you have interest in these mathematical formulations and challenges, and even the numerical challenges, then the Ian Goodfellow book is pretty good for this, and I can point you to some readings. But anyways, what's happening here is that we have a Gaussian noise that produces as latent vector z, and you can see this like ellipse here as some sort of like distribution area that represents px of z, or px given z, okay? And here is an image of what the discriminator is trying to do. So now I have this fake distribution that I'm modeling through my generator, that is this reddish area here. And I have my real distribution in blue here. What the discriminator is trying to do, the discriminator is a classifier, so it's trying to separate the space. So it's always trying to separate these two regions. Okay? And what I want to do is to get this fake distribution to get as close as possible to this real distribution over training. So how do you train these models? We call this adversarial training because, as I said, we're going to first train one model, the discriminator, make it better, and then we stop it, and then update the generator a little bit, and then go back to the discriminator, train it for a little bit more, and then generate, and then update the generator. So we are going to train these models back and forth kind of thing, right? Separately in a way, but the procedure itself is what is connecting them, right? We first train one, and then I train the other. And I keep doing that. So they're going to converge eventually. And hopefully we're going to converge to a generator that can generate real images, and a discriminator that cannot tell them apart anymore, because they are so close. The generator is making so realistic images that it's impossible to the discriminator to just do better than a random guess, right? Say, because it's 50-50 chance now. I don't know. They are so similar that I don't get what is the difference. Okay. But this is a pseudo algorithm for training again. So you're going to have a number of epochs that you're going to define. It's our common hyperparameter. And we're going to do this in mini batches because we want to train a large data set. So we're going to assume, let's say, millions of images of cats. And you want to split them in mini batches, let's say of size 32. So we have 32 images, realistic images of cats, real images of cats, right? And here's the first difference, I guess. So line number 3 here is that we normally train the discriminator for a little bit, more than the generator. And the intuition here is that if the discriminator is not good enough, the generator cannot get better. So we need at least a decent discriminator to optimize the generator. So we just give it more chance. So we have another 4 here. Let's say we're going to have k equals to 5. So we're going to do 5 training updates on the discriminator and just 1 on the generator. This kind of thing, okay? And the idea is here to kind of like always have the discriminator a little bit ahead of the generator, because we really want to make it hard for the generator, right? So otherwise you run in the risk that in the beginning of the procedure, they converge very quickly, and then that's not your goal. What you need is a very good generator. You don't care about the discriminator, actually. At the end of the procedure, you throw away the discriminator. It doesn't really, that's not our goal. Our goal is to get a good generator. That's why we normally do that. So, but in theory, this k can be equal to 1 if you want. And then you would just train once. Okay, so it's flexible. I'm just saying that in practice, people train the discriminator a little bit more than the generator every time for each mini batch. So how do you train the discriminator? And you do that first, okay? You're going to take m real examples from the training data set. That's easy, just like data loader. You get your data loader, get your m real examples. Let's say 32 images of cats from your data set. And then you're going to generate M fake examples using the current generator. So initially it's just random. So you get 32 random noise and you get 32 cats. So it's going to be very easy for the discriminator to classify this as realistic or fake. Because on one side you got a bunch of noise and one side you got a bunch of very complicated like cat-looking pictures, right? So it's easy for the discriminator in the beginning to get good accuracy in this. But it's very hard for the generator in the beginning to start getting better. But anyways, and then you update your weights. And you're going to update only the discriminator weights in this first pass. Inside of this loop here, you're going to update only the discriminator weights. And the loss here is just a binary cross entropy loss, right? Because it's a binary problem. I have real label, I have fake label, right? I want my discriminator to get good predictions. For real images, I want it classified as real. For fake, I want to classify as fake. So this is a regular binary cross entropy loss. Okay, so you do this a couple of times. And after these case steps, your discriminator is a little bit better. So remember that initially your discriminator is also random, but then you train it, let's say, 5 times. And so it's not random anymore. It got maybe now it started with 50% accuracy. Now it's, I don't know, maybe 65% accuracy or something after these 5 steps here. And now you, at line 7, your discriminator is a little bit better. So you're going to generate new samples now. And you're going to update now only the generator based on how well they fool the discriminator. And we can formalize this as a maximization as well. But you can use a BCE loss here in practice. And I'm going to tell you, it's a very cool idea. Because here you want to actually, it's a kind of an inverted BCE loss. And I'm going to show you that in code. This is an implementation in PyTorch of a GAN. And this is exactly that model, DC GAN, which uses a CNN. Okay? And here they are training again to generate faces of people. So they have this data set of famous people. So this is the generator, and this is exactly what is in the paper. This is images from the paper. I can show you the paper later. This is the generator. Okay, so you start with a random Z, and you get an image at the end. And this is the generator implemented. You have your transposed convolutions here, some batch norm, and ReLU activation function. So it's just a sequence of transposed convolutions. This layer, and then another layer, and then another layer. So it starts with a 4x4, then it grows to 8x8, then 16x16, it gets to 32x32, and eventually to 64x64x3 image. Okay? So that's what the generator does. Okay, this is just testing and handling GPU stuff. And then you get the discriminator, which is just a regular convolutional neural network with leaky ReLUs. And in the paper, they discuss some guidelines, and I can show you that later. But they use leaky ReLUs here instead of ReLUs. And I don't remember exactly why, but we can look at the paper. But anyways, here are just regular convolutions. So you take as input a 64x64x3 image, and then it shrinks down to 32x32, then 16x16, then 8x8, then 4x4. And then you get a vector at the end, and that goes into your sigmoid, and you get a prediction. Okay, that's what the discriminator does. Okay, so here's just creating the discriminator, GPU handling. Okay, that's it. Initializing the weights. Okay, so let's get to the loss function. And I think it's easier to look at the code to understand what the loss function is doing. So the optimizer, so I have two, this is cool. Yeah, so I have 2 different optimizers here. This is the difference, right? Because I'm gonna train this thing separately. Like I'm gonna have one optimizer for the discriminator and one for the generator. Okay? So I want to train them independently, but as part of the same game, right? So that's the thing. And my loss here, just see like it's a BCE loss, it's binary cross entropy. Okay, so that's the loss function we're going to use. And here there's some explanations of how they formulate this as a min-max game. But if you get to the code intuitively, it's much easier to understand, I think. So here you're going to maximize this log likelihood, which is the same of minimizing the BCE loss. And look here, this is nothing, this is just restarting the gradient. This is just sending the data to the GPU, okay? And this line here is creating a vector of labels. And what kind of labels? I need a real label. So because I am getting real data from the mini batch, okay? Where is the real data? Is here, okay? So data 0 comes from here, right? This for loop here is over the mini batches. I have a data loader here. Oh my bad. I have a data loader. So this variable data is a mini batch, okay? And I'm not going to use the label of the image, okay? I think that data set maybe has labels associated to it. The face data set, maybe the name of the person or something, or if it's male or female or whatever. But we're not going to use that. So we're going to only get the data 0, which is the X, which is the features of that image, the actual pixel values. Okay? So that's my real images here. And then I'm going to generate some labels. Those are true labels. So I'm going to call this ones. So for each image, let's say I have 32 images. For each image, I make a 1 label. So I'm going to have 32 ones here. Because they are all real images. I know they come from the data set. They are real images. So I'm creating this torch.full function. It's going to make me a vector of this size. This is a batch size. So let's say batch size is 32. So I'm going to make a vector with 32 number ones. And why is it number 1? Here, look at the real label. It's set to 1 here. Okay. So now I have a vector with 32 ones, like this. Let's see. This is going to be my y equal to np ones, maybe 32. I have a vector like this. These are my true labels. Okay? Because I have 32 real images, so they are all ones. Okay? So to compute the loss, I need some sort of y hat, right? And the y hat are my predictions that are here, which is the output. They come from the network D, which is the discriminator. So I'm going to get my images. Real CPU is the images, so I have 32 images here. Okay? And I'm going to have a prediction for each image in my mini batch. So net D is the discriminator network. And real CPU is 32 images. So it's something like this. 32 by width by height by 3. This is what that vector, this tensor looks like, real CPU. I have 32 images that are width by height in size, and they have 3 channels, RGB. And my y hat is something like this. So it's a prediction from the discriminator, and I have 32 predictions because I have 32 images. And I'm going to compute now the BCE loss between these two, between the true label and the predictions. Okay. And this is my loss. This is the loss of the discriminator because it's trying to separate real images from fake images. Here's a twist I forgot to mention. It's just an implementation detail. Instead of compact, I forgot to mention that. We would need technically this. We would need something like this. Y hat real, and then NP1's 32. And then we also would need something like Y hat fake. NP0's 32. Right? Y hat real is this, and then Y hat fake is this. Oh, sorry. Fake is this. I would need to make a mini batch of 64 and combine fake and real images, right? To then train the model. In practice, people actually first do a forward pass on all realistic images, and they do another forward pass on all fake images, instead of combining the two and doing one forward pass. Is this clear? Is that a reason? I think it's just easier to do that, and then you keep the same mini batch size. So because then your mini batch would become double the size you set it initially, right? So if your set was 34, it would actually be 64, not 32, right? This is one reason. So if you see here, it trained with all real batches first. And this is still the discriminator, right? This is that for, and this is not even like training, this is not even having this for here. So it doesn't do that. It's just trained with all real batches, with all real examples from the mini batch. And then it does the same thing, but now with all fake images. So here it first generates the noise, and then it sends that noise through the generator to get the fake images. And then it generates my labels with all zeros. Fake label is equal to 0. So then it generates the labels like this, like I just did, and computes the predictions again. But now on the fake images. But look, I'm actually not updating the weights. I only update the weights here. Okay? And I'm summing the two errors before updating. So I get the loss on the real images, I get the loss on the fake images, and I sum both of them. This is my actual loss, and I optimize that loss. Okay? Here I'm getting the gradient, right? So error d fake dot backward is getting the gradients for the fake mini batch. And error d real dot backward is getting the gradients for the real mini batch. So if I sum both of them, I get I sum of the two gradients, so now I have the combination of the gradients, then I update my model. So it's just a different way of implementing what I just said, okay? And you will see this kind of code very frequently, so it's good to look at it first together here. Any questions? Does it make sense at least? Okay. And now I update the generator. And here is the cool part, is that the generator gets better when I can fool the discriminator, right? So what happens here is I'm going to first of all restart the gradients of my generator. So here I'm going to do a new update. Okay, so I have to zero my grad. And this is the trick. I'm going to make my labels so as real labels, even though I'm producing fake images. So here, for the generator, what I'm going to do is I'm going to tell the generator, you want to get as close as possible to real images, right? So I'm going to make a vector full of ones. So I have my fake images here from before, okay? Here, my fake images. They're here. Now, at this point in time, my net D is a little bit better because I did this optimizer D step. So I updated the weights of the discriminator here, not the generator yet. So at this point in time, my discriminator is a little bit ahead of my generator. Okay? And what I'm going to do is I'm going to say, I'm going to create labels equals to 1, and I'm going to pass the fake images to the discriminator again. But the discriminator is a little bit better now, so the predictions are going to be better. Okay? So these outputs here are my predictions of the same set of fake images, at least in this implementation. You could regenerate the images if you wanted. But your predictions are a little bit better. But look at the trick. Now I'm getting the output of the discriminator and comparing against ones, real labels. Okay? So what this is doing is I'm giving fake data and trying to minimize the difference from that prediction to 1. And that's the error I'm going to use to train the generator. Okay, here. So I'm going to, here's the trick. I'm using, that's the point, Guilherme, you asked. Right? I'm actually flowing the gradients all the way from the generator to the discriminator at this point. Because the fake image, this tensor, comes from the generator. Right? It comes from the generator, which comes from the noise. So it's noise, all the computation of the generator gets the image, fake here, and then fake goes into the discriminator. The discriminator classifies the fake images. But even though I'm giving fake images, I'm telling the discriminator these are real images. So I'm fooling the discriminator. Okay? And that's the error of the generator. Because I want to fool. That's the goal of the generator, is to fool the discriminator. So the way we implement this fooling is by literally switching the labels from 0 to 1s here. And we still use BCE loss. So this is a very interesting trick to optimize these networks. And since it's all CNNs, it's all differentiable. So it all works, okay? You can compute back propagation here with no problem, okay? And here's the intuition of the training procedure. So we start with these two independent distributions. This is the fake distribution, the one in red, and the blue one is the real distribution. So they start in different regions, right? And the bar here is the discriminator. So initially, the discriminator can separate the two of them very easily because the images, the fake images are so different from the real images that it's very easy to separate them. But then you're going to do one gradient descent update, right, which is this yellow arrow here. And then your fake distribution is going to switch a little bit. It's going to actually get a little bit closer maybe to the blue one. But here you can still separate the two of them very well, okay? And then you do another update, and now your distribution is here, and your discriminators still separate them perfectly. But then eventually, they're going to start to overlap each other, and then the discriminator cannot separate them anymore. Okay? That's what's happening under the hood. And there's even, I think there's a little video here that shows that. Here is the loss of the model on the left. And on the right, you can see these two distributions, the yellow and the green. And the green is the real data, or is this is the probability density, right? So this is a normal distribution. Initially, we have this generated, the synthetic distribution, and it's going to start to get as close as possible to that real data, okay? And here are some results from 2015. These are the real images we saw. And these are fake images. From far away, you cannot judge much, right? But yeah, there is some artifacts. The faces, like, they resemble faces, but some of them don't make much sense. They have a lot of noise. Some of them are actually pretty good. But they all have like weird artifacts, like this thing here, right? Some of them, they're very deformed. But they are not blurry. And which is actually a good thing. But anyways, so here is an evolution of GANs over the years. So this model became very popular back when it was released. And I must say that, I remember that was as exciting as transformers are today, for example, if not more. Like, people were really surprised by this. Because first of all, it was very novel to train in this adversarial way. We haven't seen that. This was kind of really different stuff. And all of a sudden, you could generate images using this procedure, and people got really excited about this. So in the upcoming years, a lot of different models or improvements were developed. Like, the first model is from 2014. And then you got DC-GAN. This is the one we discussed today. So the original GAN actually was implemented with multi-layer perceptrons, the very first one. Because that wasn't the point. The point wasn't to show, okay, what architecture to use and like what bells and whistles could I improve. It was more like, oh, does this actually work if I train this in an adversarial way? So that was the main contribution. I actually have the key contributions here. So it started very basic in the beginning with MLPs and just showing that this idea could work. First of all, you have to show that this would converge to good generators, right? And this wasn't clear. And then DC-GAN is the paper actually we discussed more today, which actually introduced convolutions to the game. Okay, so we're going to use now a convolutional neural network for the generator and one for the discriminator, and then they introduced some guidelines for actually building the generator and the discriminator, and that was a very influential paper as well. And then the next year, 2016, another cool idea was introduced, which is this idea of conditional generation. So before 2016, you could use GANs to train to generate images of one thing only. So because if I wanted to generate images of cats, I had to separate the data set of cats and then train again only on that data set. If I wanted a data set of dogs, I had to train a completely separated model with a data set only of dogs, and then I would be able to generate good images of dogs. And what the conditional GAN model did was introduce the label as part of the game. What do I mean by the label? The label of the image. So now I have a data set, a label data set of, let's say, cats and dogs. And cats are zeros and dogs are ones. So when I'm training the model, I now pass this label 0 and 1 to control the generator. So I can say, like, give me an image of a cat, give me an image of a dog. Or it could be, let's say, if our ImageNet, you would have 1,000 labels, and you could generate 1,000 types of images. So here it's a much more flexible model, because you can now have this data set with different categories, and you can just tell your generator, okay, I want a bicycle, I want, let's say, a car, or I want a person, or something. And you can train all of these together. Like, you just can have a massive data set with different categories, and then you just pass the category through your GAN as part of the game. It's not actually it's not very hard to do that. So, but it's a really nice property to be able to control the generation. Then there is WGAN that improves training stability. GANs are famous for being unstable in terms of training. By unstable, I mean you might not always converge, and there is a couple of technical issues on this adversarial training that people addressed over time. Also, there was a lot of work on trying to make this work on better, of higher resolution images, like 1024 by 1024, like StyleGAN, BGAN, and so on and so forth. And then there's even like motion generation and some other stuff more recently. So there is a long story here. There's not enough time to cover all of this. I just wanted to give you that information that if you want to get into GANs, there is a lot to read, okay? Obviously nowadays there is a lot of good materials to kind of get to this very quickly, but there is a lot of work here. Same way there's a lot of transformers coming out today. There was a lot of GAN variations like every year. Okay, here are the results over the years. So you started with this kind of black and white faces in 2014, very low resolution, and then in 2015, these are all cherry picked, right? So these are all like maybe the best outcome of the model. So 2015 and then 14 is still a little bit weird, right? The mouth here is weird, the eyes are a little weird. Here also the eyes are a little weird. And then all of a sudden, boom, 2017 you get these high resolution images that really look like realistic, but this is very, very close to like Becca, I think, right? Or some like real person, so maybe it's overfitting a little bit and generating like just copying the data set. But then it starts to get better and better and more realistic. And this is just face results because GANs historically have been studied in this kind of face domain. Okay. Sorry. So actually, that was what I had for today. This last portion of the course is slightly faster, unfortunately. Hopefully, I'll get into more details the next time I teach this, because there's a lot to cover in GANs. And ideally, in a generative model course, if you're taking just like generative AI like course, then you could get into these models very deeply, right? You can study like maybe to have 3-4 lectures of GANs, 3-4 lectures of autoencoders, and like really study this in a deeper level. But yeah, that's the end of our course, at least from me. And now it's your time to rock. So like get ready, like finish your work. Ask questions if you need me. Come to my office, or just let's set up a meeting if you need help implementing your code, or if you have questions about like how to present and things. I'm working on the guidelines of the assignment, so that's all. I'm not sure we're gonna see each other physically, but yeah, thank you everyone. If I don't see you like in person, for those of you who are here, we can. It was a pleasure giving this course for you. Thank you.